Hi class, we are now on 11.6, the combined gas law. So we're going to combine pressure, volume, and temperature into one formula. So when we look at Boyle's law shows you how to use pressure and volume, which are related at constant temperature. Charles' law shows volume and temperature related at constant pressure. But what if we have two variables that change at once? And that's what the combined gas law is. And this is the formula that is used here. So where does this come from? Well, you can see we've covered Boyle's law, we've covered Charles' law. We have not covered Gay-Lussac's law, but you can see it looks very similar. The relationship here is pressure, volume, pressure and temperature, while volume in the moles stay constant. Here in Charles's law, the pressure and the moles stay constant when we're dealing with volume and temperature, and in Boyle's law, we're dealing with pressure and volume while the temperature and the moles stay constant. So what if we combine all of this together? So let's do a problem to help you understand what we're dealing with here. A sample of gas has an initial volume of 158 mils at a pressure of 735 millimeters mercury and a temperature of 34 degrees Celsius. If the gas is compressed to a volume of 108 mils and heated to a temperature of 85 degrees Celsius, what is its final pressure in millimeters mercury? So let's pull everything out to see what we can figure out from this and what exactly is it asking. So we pull out the pressure, we pull out the initial volume and the final volume, and then we pull out the temperature. Now temperature has to be changed. So we're given variables, initial and final, for volume and temperature. We have the initial pressure, but we need the final pressure. So two variables changed, and we're now looking for the final pressure. So let's take a look at what we're going to do. We're going to plug this in with all the variables that we have and solve for the one that we don't have. But before we do that, we need to change the temperature into Kelvin. Always Kelvin when we deal with gases. Excuse me, we don't deal with Celsius. So in this case, everything, if we do this right and set it up, the two variables that change, that were given the initial and the final, will cancel out, leaving only the units for the final variable that we need. In this case, it's millimeters mercury. So it's pressure. So if we plug everything in, you can see everything cancels out, and it leaves us with the value for our final pressure. So in this case, if you've noticed, we have 5 variables, and you need one variable to solve for. So a gas has a volume of 675 mils at 35 degrees Celsius and 646 millimeters mercury pressure. What is the volume of the gas at negative 95 degrees Celsius and a pressure of 802 millimeters mercury, while N is constant? So again, let's pull out all the variables that we have, figure out what exactly it's asking for, change the temperature from Celsius to Kelvin always, and then we'll plug everything in. And what we're looking for here is, you see two variables that have changed. We have temperature, initial and final variables for temperature and pressure, and we have one variable for volume. We need to get the final volume. So we plug everything in, and we end up with 314 mils as our answer, and everything else should cancel out, which it does. A sample of helium gas has a volume of 0.18 liters, a pressure of 0.800 atm, and a temperature of 29 degrees Celsius. At what temperature in Celsius will the helium have a volume of 90 mils and a pressure of 3.20 atm? Same thing, pull everything out that we know, change everything to Kelvin. So our temperature was changed to Kelvin, it just doesn't show it here. But we want our second temperature, our final temperature, to be in Celsius. So you have to remember to change it. You cannot give it in 604 Kelvin because the answer is specifically asking for Celsius. So unfortunately, it would be wrong if you were to give 604 Kelvin. Even though that's the right answer, you need one more step to provide it in the correct units. So in this case, it's 331 degrees Celsius. That's it.